As Mandy mentioned, I'll be talking to you a bit about how we expect ocean ventilation to change, particularly in the Southern Ocean as a result of increasing stratification. And just to shout out myself here, this is a picture I took in the Arctic last fall. Unfortunately, this beautiful stuff does not happen in the ocean, but we can appreciate it anyway. But I do not need to really convince this audience, but I just want to remind everybody that the Southern Ocean is central to ocean ventilation. When I talk about ocean ventilation, what I mean is exchange of heat and carbon and other tracers between the atmosphere, the upper ocean, and the interior ocean, kind of how the ocean breathes and exchanges properties. Upwards of 40% of anthropogenic carbon and 75% of excess heat uptake that has entered the ocean south of 30 South, which really highlights how important the Southern Ocean is. And I really like this figure from Soleil, which shows that this uptake of heat and carbon isn't a zonally symmetric process. It's actually quite zonally asymmetric. Meaning that these green arrows where we have this export of water into the interior ocean are happening kind of downstream of these local hotspots. And that's not going to be the focus of my talk today, but it is something I think about pretty regularly. And so just something to keep in mind. But the Southern Ocean is changing, and with that is changing where and how and when ventilation is happening. And in particular, the Southern Ocean is becoming increasingly stratified. The entire global ocean is basically becoming increasingly stratified. What that means is there are basically more layers of density between the surface and the interior as a result of a warming and freshening ocean. And this is a nice plot which just shows how this n-squared value, which is stratification, has increased in both observations and in global climate models. And this is the Southern Ocean, but as I mentioned, this is kind of global phenomenon. And I've just separated out here, this is the trend in potential temperature and the trend in salinity. And so you can see, as expected, basically everywhere is warming. But there's this really interesting kind of separation of where it is getting fresher and where it's getting cooler. You can see in particular the Southern Ocean is getting fresher as a result of sea ice melt, and this is contributing to enhanced stratification. And stratification is just an interesting topic unto itself on these largest scales. And at these basin-wide scales, stratification of the ocean constrains future heat and carbon uptake. This is a nice figure which shows stratification index. That definition doesn't really matter, but basically increased stratification to the right. And then on the y-axis is heat uptake efficiency in the relatively far future. And each of these dots here is a CMIP5 or CMIP6 model. And there are two key things here. One is there's quite a bit of spaghetti going on here. There's not a consensus by global climate models on what stratification of the global ocean is going to look like in the far future. But there is a bit of consensus around what the pattern is, where we have this negative relationship where increasingly stratified oceans take up less heat. And so this is at these kind of global scales. And I got interested in understanding how do these changes at this basin-wide scale impact fine-scale processes across the ocean. And so when I talk about fine-scale processes, we can think of this in the way that we think about kind of model hierarchies. So our coarsest model resolutions on the order of 100 kilometers. We get the big features. We get the Antarctic circumpolar current, but we're not resolving much more than that. We can move to more coarse less coarse models, where you're going to begin to resolve features probably at the mesoscale. Then you can get more and more fine scale. And these finest scales, you're really beginning to resolve these small scale interactions. And so how do these basin-wide changes translate into what's happening at these smallest, finest scales? And just to give you an image of what these finest scales really look like, this is ocean color from NASA. In the gray are clouds, in the dark blue is background ocean, and the greens and light blues are plankton, a plankton bloom. And so you can see plankton doesn't just bloom in these like kind of amorphous blobs. Plankton blooms are really shaped by and stirred by surface ocean physics. And you can see that happening all in here. And I'll be using a couple of terms throughout the rest of the talk just to introduce them to you. If you don't think about this regularly, we have processes going on at the mesoscale. These are scales where Rossby number is much less than 1. I put up the state of Rhode Island here, where I currently live, just to give you a sense of either how big these processes are or how small Rhode Island is. And then we also have processes that are significantly smaller, but are still energetically forced by the mesoscale, and we call these very creatively the sub-mesoscale. And these are processes where the Rossby number is order 1, and you can see we get these really fun filamentary structures. And these processes, these sub-mesoscale processes, evolve on the timescales that are really relevant for biology. And so if you're thinking biophysical interactions, these are the processes that you get really excited about. So just to give you a sense of why we would care about thinking about ventilation at these smallest scale processes, I'm going to chop into one of these eddies. It's kind of like I'm going to make a nice slice of cake and just show you what some data shows that ventilation can do, or what ventilation is happening at these finest scales. So in this plot, which is a little too busy, I'll try to walk you through it. We have a mesoscale eddy that's spinning around. And what we have done here is we're looking at a couple of different float profiles. And then we also had a glider that kind of made a nice slice into the eddy. So it went into and came out of the eddy. And I'm not going to introduce this variable really here, but this is basically we can think of it as a timer for how old waters are. This is apparent oxygen utilization. And in this figure, values that are in these green colors are waters that are relatively old as compared to other waters at that pressure level. And then waters that are brown are waters that were recently at the surface. And so if we're using the term ventilation, waters that are brown are recently ventilated waters, meaning they recently came from the surface ocean. So what stands out to me here is that there's this anomaly of young waters that is entering the interior ocean at the edge of one of these mesoscale eddies. And in particular, you can see that this is reaching about 300, 400 meters depth. That's pretty significant. That's deeper than the mixed layer gets in this region. And so we have it's a pretty significant chance of that water staying sequestered for a significant period of time. This is oxygen, or an oxygen anomaly, but you can think of this would probably have a carbon signature with it, maybe have heat signature with it. It has very climate relevant. It's very climate relevant. And so these fine scales and these ventilation at these fine scales may be important for carbon and heat budgets across the global ocean, but I'm going to focus on the Southern Ocean here. Previous studies have projected that fine-scale ventilation, these processes that I just talked about, will decrease in efficiency in an increasingly stratified world. So this is some nice work by Jay Brett off of Kelvin Richards' work, which looked at a present-day case and a future case in a pretty coarse model. And what's plotted here is vertical velocity. So you can imagine that in order to get this kind of transport, there's a lateral component, but also a vertical component, and that vertical component is kind of what we care about here. And so what they show is in a standard case, you have pretty strong vertical velocities, but moving into a future case, your vertical velocities associated with these small scales decrease. And they model their future case and this increasing stratification by increasing the viscosity of their model. And I think that's a nice first step, a nice first way to assess, how these processes will respond to an increasing stratification. But I wanted to understand what happens if we model stratification change explicitly, rather than using artificially increasing the viscosity of your model. So I'll talk about 3 different questions here. The first is, at these finest scales, how are tracers actually moving between the surface and the interior ocean? In other words, at these fine scales, how is the ocean ventilating? In the next part, I'll actually talk about that stratification change and how will changing ocean stratification impact fine-scale ventilation. And then the third question is a really well-posed question, but where do we go from here? So to answer these questions, I've used a setup of the MIT GCM. This is an idealized setup. But what we have is basically a zonally reentrant model. So you can think of this way is north, this way is south. We have a wall to the south, which I like to call Antarctica. We have to the north a sponge layer, which is always resetting to our temperature profile. And what goes out is what comes in and forces. And so our model is forced by a sine wave, a wind, and which is constantly creating this front in the surface ocean. And we also have some surface cooling in order to enhance our mixed layer depth. And we have modeled we have produced our model to kind of mimic the Antarctic polar front. The dotted lines here are observations from Argo. The solid lines are from our model. For only using temperature as an active tracer, I think we did a pretty decent job of mimicking the polar front here. And what's really important is that this model is at 1 kilometer horizontal resolution. For those who aren't used to thinking about ocean models, that's pretty high resolution. And that means we're going to be able to resolve these small-scale processes, the majority of these sub-mesoscale processes. And we've run even more fine, high resolution to check, and this has done a good job of capturing the processes we're looking at. And I would be remiss not to mention that the slope of the front in our model is a function of both vertical density gradients and also the lateral density gradients. And what's important, why I mentioned that, is one of those things is the thing we're attempting to change. And so stratification is this vertical buoyancy gradient. And if we change that, we're definitely going to change our slope. And you can imagine if you change your slope of a front, you're going to change the amount of energy that's available to that system. So we tried a bunch of different scenarios. I have all of those different scenarios I could show you. The model runs I'm going to show you today are cases where we kept our front constant, the slope of our front constant. The way we did that was when we increased our stratification, we also increased our lateral buoyancy gradient, and vice versa. But we also have the case where we increased stratification, but we held our lateral buoyancy gradient constant. And quite frankly, we do not yet know how the Antarctic circumpolar current is responding to a vertical density gradient changes. And so all of these runs are useful. As I mentioned, we test a couple of different stratification regimes to observe changes to ventilation. We have our baseline case. We have a decreased stratification case, which I have not seen as super physical, but it is useful to have an end member. And then an increased stratification case. And this change from baseline to increased stratification is about the change we expect to see in the next 30 years as a result of a warming ocean. So to test how tracers, you can think of surface heat or carbon, move from the surface to the interior ocean, we seed a passive tracer in our model. Once we let our model spin up and we seed tracer and watch where it moves. And then check in a few days, model days, to see where it is. You know, if you see tracer there, that it has to have originated at the surface. You can think of tracer in this model as a dye, like you're just putting dye on the surface ocean, or you can think of it as pink phytoplankton, if that's more your style. So I'm going to show a couple of different movies here, but I just want to introduce what we'll be looking at. So we're first going to be looking at our model run at the surface. And so we're going to be looking at vorticity here on the left, and then at the tracer field on the right. And of course, since we're seeding at the surface with our tracer, it's going to start as bright pink, and then it'll evolve from there. So what I want you to watch for is check out where the tracer is preferentially converging, where it finds itself. And I'll let it run again, but we'll, when it restarts, watch where the tracer preferentially finds itself. Is it congregating in cyclonic purple features or in anticyclonic orange features? Oh, thank you. I usually do like an active learning thing. But yes, I agree. I think it's also converging in cyclonic features and these purple features. Something different, well, that gives it away. Something different happens when we move to depth. This is at 350 meters. And we're looking at the same fields here, vorticity on the left, tracer field on the right. First of all, what happens is tracer is penetrating to depth. It's not falling down like a sheet of, just pink coming down. It's penetrating. It's really punctuating to depth, particularly at the edges of these gray outlines, which are density field outlines. And you can really see those punctuating. But now I want you to pay attention to what color the tracer is associating itself with. Kind of already gave it away, but the tracer at depth is associated with these anticyclonic vorticities, so these orange features. And so another way to look at this, you could just watch those movies all day if you wanted to, and I have, but we can also plot this. On the x-axis is that vorticity, and on the y-axis is depth. And as we saw in the surface, tracers preferentially trapped within cyclones. And this aligns with what we've seen in observations, what we see in, just fields of phytoplankton from ocean color observations. But at depth, that is where you preferentially see a tracer within these high anticyclonic values. So that means somehow you have moved your tracer that was preferentially trapped within a cyclone. At depth, it is preferentially trapped within an anticyclone. And we can see this not just looking at tracer concentration, but also looking at tracer flux, which might be a more interesting metric. Again, in the mixed layer, we have tracer that's preferentially moving downward in cyclones, but outside of the mixed layer, your tracer's preferentially moving down into the interior ocean in anticyclonic features. So what's actually happening here? We actually are able to use a relatively simple argument to understand how this transition from tracers trapped within cyclones move into anticyclones. And so you can think of this the same way that probably in atmospheric science class, you learned about potential vorticity and how when when an air mass goes over a mountain range, its potential vorticity has to change in order to stay conserved. And so we use the same argument here. Basically, our mixed layers in this model are pretty deep. That's generally true across the Southern Ocean, at least north of the polar front. And when our tracer gets subducted into the stratified interior ocean, it goes from having a certain height associated with the mixed layer, into a significantly shorter a density layer. And so in order to conserve potential vorticity, which is this F plus zeta on H, if you decrease H, you also have to decrease zeta. And the math works out where if your height decreases enough, you can flip the sign of the relative vorticity. And so we go from being in a cyclonic feature to an anticyclonic feature solely as a result of moving from a pretty deep mixed layer into the interior. So this is all to say that subduction or ventilation is occurring at these steeply sloping density surfaces, and that when we look at observations, these anticyclonic features within the interior ocean, within the ocean's pykmocline or thermocline, these anticyclones are the physical subsurface signature of recent subduction. This is just a movie showing the formation of this kind of bolus of tracer at 300, 400 meters depth and how it's associated with those anticyclonic vorticities. So now that we know kind of what the mechanistic, how tracers actually getting from the surface to the interior, how does changing stratification impact this ventilation? And these are just screenshots of our model runs. Remember, we had decreased stratification, a baseline, and an increased stratification case. And already can maybe begin to tell a bit of the story going on here. I see significantly more tracer. This is at depth, but I see significantly more tracer in this case than I do in these cases. But looking at this in a slightly different way, what we're going to be plotting here on the x-axis is initial stratification in our simulated Southern Ocean. Where this value here is our present day Southern Ocean, although I should mention it's a very heterogeneous field, but this is, an average of an average of an average. And moving this direction is increasing stratification, so moving into the future. On the y-axis is not trivial, but it's the amount of tracer flux. And so basically, the greater the value, the greater the magnitude, the higher the downward flux. So the more movement of tracer from the surface into the interior. So when we look at the decreased stratification cases, remember this is our present day case, this is decreasing stratification. I think that this is a relatively easy story to understand. We see that at both 250 meters depth, 350 meters depth, the signature kind of goes away beyond that because it's way too deep to penetrate. But at these depths, decreased stratification leads to enhanced tracer flux. The way I think about this physically, it's like in this present day case, you have 5 pieces of paper and they are separated an inch apart from each other. It's going to take a certain amount of force to punch through those 5 pieces of paper. In the decreased stratification case, it's like you spread those pieces of paper out. It's going to be easier to punch through that stratification, those pieces of paper. And so that's how I physically understand this relationship. things get very interesting when we move into an increasingly stratified, increased stratification, so into our future. This relationship, if my analogy held true, you would think it would become harder to move tracer into the interior ocean. In reality, what we find is that there's this kind of plateau or saturation of the amount of tracer flux into the interior at these depths. And the way we explain this and understand this is that this is, again, looking at tracer flux, and this is across the whole domain. This is the same as the pink line that I just showed before. But now we're going to look at the flux associated just with those anticyclonic features. And so looking at this, what's plotted here is the flux associated with only strongly anticyclonic features. So these features with a really low Rossby number. So as we expect and saw in our previous results, these strongly anticyclonic features are dominating downward fluxes, particularly at depth. But what's really important is that the number of these features goes up significantly in these decreased stratification cases. So again, this is present day, kind of baseline case. In decreased stratification cases, we have a greater number of these strongly anticyclonic features, suggesting there's more of these fine-scale ventilation processes happening. But moving to increasingly stratified conditions, we don't have a change. Basically, we are kind of at this limit where we have, are able to take up tracer by these fine-scale motions. So what's changed here, our previous understanding was that, moving into the future, increasing stratification is going to result in reduced vertical velocities, reducing fine-scale ventilation. What our new understanding is, hopefully, is that our changes in ventilation are actually nonlinear with changes in stratification. And particularly if you are explicitly resolving stratification and fine-scale motions. In particular, and I'd love to talk more with folks here, our present-day Antarctic circumpolar current and its density structure may represent some kind of inflection point in this context, where we move from a place where fine-scale motions are really responsive to stratification to where they are not. So where do we go from here? There are a couple of questions that keep me up at night, and I'd love to talk to any of you about any of them. The first is, how is the slope of the Antarctic circumpolar current really responding to warming and freshening? This is a question that I don't think has been, really resolved within the community, but has real impacts. This is basically the most recent paper that's kind of tried to address this question. And they found that basically the slope of the Antarctic circumpolar current is holding steady with changes in warming and in salinity. But this is, as you can tell, it's been a couple of years now, and I think there's still a lot of work to do in understanding if the slope of the Antarctic circumpolar current is staying constant, and if so, why. Next, and this is something that was mentioned earlier, but how do we get around the fact that it's not going to be until 2040, 2050 when we're able to explicitly resolve fine-scale motions in global climate models? This is a really nice plot from Hewitt et al., which shows 1980 to 2025. On the y-axis is horizontal grid spacing of global climate models, ocean resolution in particular. And you can see that, yes, models are getting more and more high resolution, but as I mentioned, it's going to be a little while till we're able to resolve these 1 kilometer features, 1 kilometer and smaller. And so how do we parameterize these processes without resorting to changing viscosity and doing very somewhat falsified things? And then the third question is, what about carbon and biogeochemistry? What about it? But in particular, what plankton species are being subducted within these features? You know, the kind of thing we actually care about is carbon fluxes and carbon storage and carbon sequestration. And so what are the actual species that are being transported into the interior ocean? And what does that mean about carbon storage? And I just add these figures up here to kind of convince you that these fine-scale motions, in this case subseasonal motions, play a pretty dominant role in explaining chlorophyll variance. This is within the Southern Ocean, but that's globally true. And so we need to understand and better observe these subseasonal processes in order to better understand what the future of carbon and heat in the Southern Ocean will look like. I'm really grateful to have phenomenal funding and also to have phenomenal collaborators, but I am excited to take any questions you have.
Excellent. Thanks so much, Lily. Okay, time for some questions. Nicole, you got one? Great.
Hi, thanks for the talk. It was really nice. I have two questions. The first one is, why is the stratification changing in the Southern Ocean? And the second one is, probably you said it, the way the tracers get sort of like stuck in the anticyclonic features and then like subduct. Why are they picking the anticyclonic features?
Yeah. Okay, so starting with why is stratification changing? Sorry, I am one of these people. Okay, the first reason is basically the heat at the surface, and also in the Southern Ocean, the freshening just makes it so the surface is warmer and more fresh than it previously was, but the deep ocean isn't changing as fast. So you're basically adding more layers of density in between the surface and the interior. That's happening pretty globally. There are some, counteracting measures here due to salinity being funky. Yeah, that's why stratification is increasing. Does that make sense? Okay. The second question is why tracers being kind of trapped within these anticyclones. What we think is happening is basically tracer is preferentially congregating within cyclones in the surface ocean. That's not really a new discovery. That we see that in observations, but that basically we know that at sharp density fronts, tracer we can get strong vertical velocities that move tracer from the surface to the interior. But the interior ocean is more stratified. These layers of density are significantly thinner than the mixed layer. And so you can you get that trapping of water that has a certain potential vorticity aligned with it that was assigned at the surface. It gets squashed, and so therefore it spins down.
But do you know, why does it pick, I guess, cyclone versus, why does it pick one polarity versus the other in the first place?
Yeah. At the surface, cyclones are just areas of, kind of this convergence of water. But then, and then the idea is you have in these cyclones, you will have at the, what's a good, okay. Say you have your tracer trapped in one of these cyclones. When that tracer reaches the edge of the cyclone, because it's not just going to stay trapped in the middle, that's when it can get moved into the interior.
Thank you.
Yeah, we'll talk more.
Yeah.
Okay, Rebecca, can I ask you just, could you introduce yourself so people online can know who's asking the question? Thanks.
Sure. Hi, I'm Becca Jackson. Thanks so much for a great talk. So you mentioned at the end, the debate about whether the isopicknal slopes are changing over time. And I think also you mentioned towards the beginning that you ran simulations where when you increase the stratification, sometimes you compensate it with the horizontal buoyancy gradient, sometimes you don't. And so I was curious, like the main results for the ventilation plateaus, was that in the case where you've held the slope constant? I'm curious how much your results change when you don't compensate the horizontal.
Thank you for asking a question that I definitely have slides for. So just to prime everybody, where this is our case. This is the slope of the isopycnals, which is a function of lateral buoyancy gradient and vertical buoyancy gradient. In the case where which are the cases I showed, which are the constant, oh, no, that's a lie, sorry. There are cases where we hold our horizontal buoyancy gradient constant, and that will result in a changed isopycnal slope. So if you increase your stratification, you will get in this case, a reduced isopycnal slope. The cases I showed are this case where we adapted our buoyancy gradient. And so we changed our lateral buoyancy gradient, the same magnitude as the horizontal or the vertical buoyancy gradient, in order to hold the slope constant. And so in that case, you're increasing both your lateral buoyancy gradient and your vertical buoyancy gradient, but you're holding the slope constant. Anyway, so in the cases where we held our slope constant, those are the solid lines I showed you earlier. In the cases where we allowed our slope to change, just as a result of not changing the lateral buoyancy gradient, we actually found that there was no response of ventilation, of fine-scale ventilation, that is, to changes in stratification. What's going on here, we are still figuring out, but I think is really a primer for why it's important for us to understand how the slope is changing, because these are very different responses. Although it doesn't really change in this increasing case, which is our reality, but it is an interesting scientific question in this decreased stratification case. Why doesn't where you allow your slope to respond, why your ventilation isn't changing? If anybody knows, you would save me a lot of time.
Hi, I'm Earl Wilson. So great talk, Lily. So I have two questions. So the other side of the unarctic, the isopycnal slope and the ACC staying constant is the eddy saturation argument.
Yes.
And so you have potentially in the future stronger winds, more eddy field, stronger eddies, potentially more sub-mesoscale eddies as well. Mm-hmm. So how do you think about that in relation to increased stratification? Do you think one's going to win out? And my second question has to do with your explanation for how stratification impacts ventilation. I like your punching through paper analogy, but in the SPAL schematic you showed a mostly isopycnal process. Mm-hmm. And so, yeah, could you clarify that?
Yeah. So thinking about the first question, yes. So we are seeing increased westerly winds, and we are, I think, seeing increased eddy kinetic energy across the Southern Ocean, and those two things are kind of playing out to theoretically hold our slope constant. But as you mentioned, if we have an increased eddy field, potentially more of like sub-mesoscale subduction. One thing I think is a bit of a complicating factor here is that when you increase your stratification, sorry, I'm doing a lot of math back and forth here. When you increase your stratification, what stands out to me is that potentially you can still subduct below the base of the mixed layer, but it's not as far below the base of the mixed layer as you would be able to do in the baseline or decreased stratification case. So basically, I think potentially, yes, you could have increased subduction by fine scale motions. But long term, if you're not subducting as deeply, will it really matter if that carbon is just reventilated next winter? That doesn't really answer your question, I don't think, but let's talk more. What was the second question?
I can ask you later. So.
Okay.
I'm too short, sorry. Camille from Inframer. Thanks for the talk. My question is kind of a follow-up from Nicole, because I'm not sure I get all the bits and pieces of your mechanism to subduct. The argument you're making there exactly, I mean, I understand you're going to increase your PV, you're going to increase your vorticity to conserve PV.
Yeah.
But that doesn't really explain why you go from a cyclone to an anticyclone. And then if you look at your movie, I mean, if that argument is basically you transfer when you subduct under the front, your movie doesn't really show a super strong relation with the front. So you get basically subduction and trace a bit everywhere in your domain. Yeah. So I don't really get the detail of what's going on there.
Okay. So let me address the second part first, which is this is a common challenge within the community where we think about fronts on many scales. So we're thinking about the Antarctic circumpolar current, which is made up of like large jets, which we call fronts, kind of colloquially. And that's what, we're looking at. That's what that black line is. That's where we're definitionally defining our polar front in this simulation. But we also have these small scale fronts, like little density fronts. In our field, and that's basically where these gray contours are places where you have like small scale density fronts, just as a result of having warm water next to cold water. And so the subduction is happening at those small scale fronts, but those small scale fronts are being fed by the fact that there's this large scale front, which is feeding to the mesoscale to the submesoscale. So does that address that kind of part? Okay. And so, but then thinking about the first part of your question, could you remind me what it was?
I mean, you showed that kind of to explain why you go from a cyclone to an anticyclone. And I understand you will change vorticity to conserve PV, but that doesn't really say why you would change sign.
Yeah. The idea is that you're just flipping the sign of zeta will not flip the whole sign of this. F is still a significant part. And so this can become negative, but the whole value remains positive if, H is small enough to counteract.
But you do see that as like the same feature being subducted.
Yes, it is. We do have to account for the fact that we do have surface cooling, so we are introducing some, PV at the surface. But we do see that this holds within our example here. So if we move from a cyclone which has, say a Rossby order or Rossby number of 1 as a cyclone, this water here could have originated from that cyclone because our change in height is so extreme.
Do you have time for 2 more questions? Let's have Ellen and then Henri.
Okay, yeah, mine will be quick. Ellen Buckley. So you said that there's different amounts of stratification across the Southern Ocean. Yeah. Are there observations of surface water subduction in different amounts of stratification that you can compare with modeling results?
Yeah. So, oh my gosh, you guys are asking the best questions. One way we look at this, so this is some work done by Maggie Gonzalez recently that we just published. Our focus was slightly different, but we ended up finding similar, something that related to this work. What Maggie is plotting here in the color in the in the circles are winter water, and so that's basically just water south of the polar front. But in the triangles are these anomalies of low stratified, low water with low internal stratification in the interior, which is a signature of what we found. So basically, this is what we found, but in observations. And you can see that this is not, they're not found everywhere across the Southern Ocean. In particular, these anomalies of low internal stratification, or these anticyclones, basically, are found at the polar front. And also, if you're familiar with looking at the Southern Ocean, they're in these regions of high eddy kinetic energy. And they're also in generally low stratification environments. And so this is, to me, some nice observational evidence of what we found in our model. There are many debates in the community around, the sources of these low internal stratification features. I think I have the right answer. We can talk more about this.
All right, Henri, last question.
Yeah, thanks. Really cool simulations.
Thank you.
Can you talk a bit about how the transient evolution works? So, for example, I can't remember off the top of my head if when you change the stratification and the horizontal buoyancy gradient such that the slope is constant, if that means that the time scale of instabilities is constant and also the spatial scale. And so how do you account for all of that?
So we ran simulations not only where, m squared on n squared, so the slope was constant, and then cases where we held m squared constant, but also cases where the Richardson number, we held constant. I don't have those plotted up here. But yes, what you're mentioning is really important, in that by changing our lateral buoyancy gradient and the stratification, you are changing basically the rate at which instabilities can form. That's a much longer conversation I'd love to have with you offline, but basically we think that we've corrected for that by holding Richardson number constant in some of our other simulations, and seeing the same response as we saw in the constant sloped cases.
Thanks.
Yeah.
Okay, thanks again to Claudia and Lily. We have coffee and cookies back here at 4 o'clock. All right, thanks everyone.